Are you seeing my screen? Not yet.
I am not seeing it yet.
Not yet. Okay. All right.
So just showing your name.
All right. So let me share screen. Okay. So the first question here, it says a bullet of mass is fired horizontally with speed at a wooden block, a different mass resting on a frictionless table. The bullet hits the block and becomes completely embedded within it after the bullet has come to rest within the block. It's traveling at a speed. Okay. So what kind of collision? Which drawing best describes the collision? So it's elastic or inelastic. B is ridiculous. It's either perfectly elastic or perfectly inelastic, I believe. You happen to know without me looking which one this is, because I have to look up the definitions for each of these.
I do not know.
Okay, so there's different types of collisions. One where like things like momentum and energy are conserved, and then ones where they're not.
All right.
So it depends on what this has to say here. All right, so the trying to find a decent resource here. Okay, elastic versus inelastic collisions. Start there. Okay, so a perfectly elastic collision is one that's defined when there's no loss of kinetic energy. That is usually, I mean, that's usually not the case in reality, but I want to say that this is a perfectly elastic collision. Do you want to try that for part A? That's because there's no friction, comes to rest, it travels.
Oh, wait, it says incorrect. In perfectly elastic collisions, the colliding objects bounce off of each other with no loss of kinetic energy.
Okay, so then we'll go perfectly inelastic here. So the change in some other form of energy in the collision.
That's correct.
Okay. So then in a perfectly inelastic collision, what is conserved?
Conserved. Is it just the kinetic energy? What do you think?
Say that again.
I think it's the kinetic energy, but I have no idea.
I mean, these are just momentum is conserved, but kinetic energy is not. So momentum only in this one.
All right, I think it's momentum. Okay, momentum.
Yep. Momentum correct. Only. Yeah, momentum only. Okay, so then part C, what is the speed of the block after the collision? Express your answer in terms of V, I, MW, and MB. Okay, so the basics of this here is that you've got V1 MB plus, and then the mass of the wood, but it's not moving, so it has no velocity.
Yeah.
And then they're together, so it's the mass of the bullet plus the mass of the wood times the velocity final. So what is the speed of the block bullet system after the collision? So we're solving for V final. This goes to 0, so your V final is that's an I. It's an I, VI MB over MB plus MW.
What's MW?
Mass of the wood.
Mass of the wood, okay. And mass of the bullet. Okay. Initial velocity, mass of the bullet. Okay. So what are we given in this equation? We are given just that, right? Hold on a second. I gotta turn off my dark mode extension so that I can actually use the symbols and stuff for this. For whatever reason, that screws with it. Go back. Should I make the I little, or how should I do it? Is it like V little I M little b? What do you think?
Say that again.
So when I'm setting this up into the computer, should I do V little I and then M little b?
Yeah,
Do that?
it's underscore, but there's a but then there's a button to do that on the.
Awesome. I was just checking so I don't like get it wrong. Let's see. And then we got little b. All right, that's correct. Let's get moving.
All right,
What's
so
next one?
I'm looking at the next one here, starting from rest and iron block. I'm not going to copy it because it's all multiple choice. We can I'll try to give the information here. So the
Is
part
the block
A,
and the magnet one?
yes, the magnet one.
Okay.
So we've got an iron block. So it's on some sort of a hill. It's on some sort of a hill,
Mhm.
and then it slides down a friction cell of height h.
Okay.
Height h. At the base of the hill collides with and sticks to a magnet with mass m. So the magnet's down here. It's not doing anything, but then it hits and comes together. So the there's energies associated with each of these objects. So the one on the top of the hill has a potential energy, but it's not moving, so it doesn't have any kinetic energy. Sometimes you write that kinetic energy, which is 0. And then later on, it comes down the hill. All that potential energy is converted into kinetic energy. And it says that it's a completely inelastic collision between the two. So I'll try to run through some of this. I mean, it's like this comes down, hits, and then there's an inelastic collision right
All
there. But I'm looking up the reference to this. So the potential energy is mass of the block B, GH. Okay. And then that equals at the bottom of the hill 1/2 the mass of the block, the velocity of the block squared. So the mass of the blocks cancel out, and when you solve for VB, you move the 2 over, or you clear the 1/2, so you get 2GH square root. All
Do you
right.
multiply it by anything?
Well, we're not done yet. So that's right before, that's the instant before it collides with this.
Oh, okay.
Okay, so the instant before it collides with that, it's going that fast. So right before it collides, there's the mass of the block times the velocity of the block. This is the momentum equation.
Okay.
Plus the mass of the magnet times the velocity of the magnet, but it's not moving, so it's 0. They stick together. So that means the mass of the block plus the mass of the magnet are together. And then they've got a final velocity V, we'll call it.
Oh, okay.
Okay. So the VB is up here. The VB is the square root of 2gh. So we're solving for big V. So big V is the mass of the block times the velocity of the block over the mass of the block plus the mass of the magnet. VB though is really, so this is M, little m, uppercase B,
Okay.
or little m, uppercase B plus little m, uppercase M, square root 2gh. So whatever that option is there.
And that's correct.
Yeah. All right, so I don't know. Let's see here. Now assume two masses continue to move at the speed v from part A until they encounter a rough surface. The coefficient of friction between the mass and the surface is mu. If the blocks come to rest after a distance s, which of the following would you use to find s? Wow. So there's a lot there. This says to use the work energy theorem. The work energy theorem. So the work energy theorem here says that the kinetic energy final minus the kinetic energy initial equals the work that's done. And the kinetic energy is final is 0 because it stops after a distance s. Wow, this is complicated. Okay. So the work done by friction is the force of friction times the distance it travels, which is s. And if you remember the mass system, like they're moving together, they have a combined their normal force, which equals mg. The m in this case is really the mass of the block. Mass of the block plus the mass of the magnet times g times s. But because friction opposes motion, the work is negative. And then the force of friction has a mu in it. So force of friction equals mu times the normal force. This is the normal force right here, and then there's mu. So it's kind of drawn minus mu, mass of the block plus mass of the magnet, g times s, I've got the mu equals. Kinetic energy final is 0 because it stops. The initial kinetic energy is what we had from, it's 1/2 mv squared. So it's the mass of the block plus the mass of the magnet. And then it's the velocity we just found, which is mb over mb plus mn times the square root of 2g big H, all squared.
Okay.
Yeah. So and then s, you're dividing. So since you're solving for s, the mb plus mn's cancel out on both sides. The negative cancel out. The mu goes to the bottom. Oh no, they keep it there. Minus mu gs mb plus mn gs. Okay, so they're showing the answer is C as being correct after all that. I think.
And that is correct. Let's move on.
All right. Okay, so I'm up to the superball collides with the table.
Okay.
Superball with mass m equal 50 grams is dropped from a height of 1.5 meters, collides with the table, then bounces up to a height of 1 meter. The duration of the collision, contact with the table is 15 milliseconds. This problem take y, positive y direction be upward. Okay. Find the y component of the momentum of the ball immediately before the collision. Okay. So momentum is mass times velocity. And we know that, I'll make it some room here. So the ball is dropped. The ball is up here. It's dropped, boom, hits the ground. So all of the potential energy of the ball, mgh of the ball, is equal to 1/2 mv squared. So the velocity right before impact is the square root of 2gh. And the momentum, p, is mass times velocity. So it's the mass of the ball times the square root of 2gh.
All right.
So we can get these. So the mass of the ball is 50 grams. So it's 50 over 1,000 because it's got to be in kilograms. Square root of 2 times 9.8. The height is 1.5 meters. And the units, they already give you the units. Thank goodness.
kg times m divided by s?
Yeah. 50 divided by 1,000 times square root 2 times 9.8 times 1.5. So I get that. I really probably should check this question because I mean, before we go much further, but
It says your answer implies that the momentum is directed upward.
okay, so it looks like it's reasonable. The 0.27 is that what you got?
It says incorrect. Your answer implies that the momentum is directed upward.
So that means it should be negative.
And that is correct. All right, find the y component of the momentum after the collision.
All right, so now we're moving here a little bit. Why in the ball immediately after the collision? Okay, so after the collision, because it hits the ground, it loses some. There's an impulse, which is the okay. So according to the law of conservation, final energy, G 1/2 mv squared. Okay. Which part are we doing? Immediately after the collision, just as leaving the table?
Yeah.
Okay, so according to this, this one doesn't do it. Where does that number come from? 0.05. So they do this calculation where they find the final velocity, of the ball, the height up above it, up when it bounces back up, hits the ground, comes down, comes back up, 2gh again, which is the square root of 2 times 9.8 times 1, which is 4.43. And they say that, okay, the momentum of the ball there is 0.05, its mass, 50 over 1,000, times the velocity, 4.43, and that equals 0.22. The change in momentum is, okay, so maybe that's what it wants. Part B. Huh. Oh, it gives us the time that it's no, that's what I just did that's something else. That's like part C probably. These are complicated. So try that 0.22 for part B.
Correct. All right, on the C.
So in part C, it wants the change in momentum. So the change in momentum is the final, which we just calculated, the 0.22 minus the initial. Now the initial is actually negative because we said it's going in a certain direction. I think it was did we say 0.2? So yeah. So that's 0.49.
So 0.49. Should I plug that in?
Yes, try that.
Correct.
Okay. Part D is the force. The force, that's why they give you the time. The force is the impulse, the delta P over the time, which is 0.49 over the time 15 over 1,000 because it's in milliseconds. So try 33 newtons.
33 newtons.
Yes.
All right. Correct. Oh, it has a part E. Did I send that to you?
You did. What does it ask for? The energy after kinetic energy after before and after the collision.
Yeah, in joules.
Express your answer numerically. Okay, so the kinetic energy before and after. So it's the change in kinetic energy. So it was the final velocity. It's 1/2. It's the mass is 0.005. The velocity is 4.43. That's the squared. Minus 1/2. The mass is 0.05 still, and then we got velocity. I guess we never calculated the square root 2 times 9.8 times 1.5. So we need to calculate that.
Okay.
Which looks like it's 5.42. And I'm getting around minus 0.245 joules for that.
Correct.
I mean, Jack, I'll just warn you. I mean, this is not learning. This is just, we're just doing problems. We're not really
Learning, yeah.
getting much out of this otherwise. So, okay, so I'm up to the billiard ball part. Billiard ball A, I'm up to that one. Is that okay with you?
Yes.
Okay. Lovely. Okay, so this one, I'm trying to find a picture because it'd be helpful. Initially, ball A is deflected off in an angle theta A. Okay, in the original direction. Okay, so the picture is really helpful here. I'm taking a bit of a guess. I was hoping to find a picture here of this, but the first one didn't have a picture. Let's see if one of these other ones does. Okay, so you got ball A here and ball B here.
Mm-hmm.
They hit, they collide, boom.
All right.
A shoots off that direction. Theta A is what is referred to as that.
That's the angle. Is that 30 degrees?
That's the angle, and then ball B shoots off in that direction. Theta B, some angle there, but it's going. That's later on, and that's later on. So you can conserve momentum in the direction of motion,
Yeah.
meaning like an X or Y coordinates. So
Mm-hmm.
A is moving, but B is not. So A has momentum. It has mass A, velocity A, and then each of these have final momentum in their direction. So in the case of A, it has mass A, velocity. What do they use here? A prime? Yeah, V prime A, cosine theta. I guess.
MAVA and MA.
Okay, yeah, there is cosine theta A plus mass of ball B, velocity of ball B prime, cosine theta B.
And
So
you
it
don't
looks
move it
like,
around at all?
say that again?
You don't move them around at all, right?
No, just that letter A is
So this would be C. All right, I clicked
VC.
on it. That's correct. All right.
Okay, so now that was in the X direction. Okay, in the
All right.
Y direction, because the ball is only moving horizontally initially, it's 0 equals because nothing else happens except on the right side. So you got mass of ball A, velocity prime of ball A, sine theta A. That gives us the Y component.
Okay.
But that's positive now, and then it's going to be minus mass of ball B, velocity prime of ball B, sine theta B. That's the going the other direction. So it looks like it's letter B is
For part B, right?
yes.
All right. All right. So now solve these equations for theta B of ball B after the collision. Do not assume the collision is elastic. What does that mean by don't assume that the collision is elastic?
I think you got to do the conservation of energy equations for like 1/2 mv squared things going in that. So let me look here. I'm looking at this thing. I mean, there's so many. There's like, I'm looking at someone else's solution here. There's like,
Lots of layers to it.
there's like, well, there's like 12 pages of notes to do this problem. It's a little bit more simple, but we need to find the velocity of B first, I think. Okay. I'm trying to find the right equation to start out here. I'm going to just suggest we move on to another question. We're not going to get through. If we won't get through anything more than this.
If we stick on it, all right, that's fine.
It's
Let's
up to you.
move on.
It's up to
Yeah,
you.
yeah. Let's just move on. Let's try to get as many
Okay.
as we can.
Okay.
This one should be much more simple.
These will go quite a bit faster. Why do they? Okay. 7.51. So that I'm not gonna snip this in because it doesn't help do that. So the cm of an empty
What do I mean by
12.
CM? Center mass?
Yeah.
Okay.
Which is weird, but that's what they did. So, okay.
All right. How far from the front of the car will the center mass be when two people in the front seat 2.5 meters away from the front of the car and three people in the back seat 3.45 meters from the front? See that each person has a mass of 80 kilograms. Express your answer to three significant figures.
So your center mass is it's the m times x plus the m times x and so on all over your m's.
Okay.
Oh, this one's not. This is weird. Okay, so in your problem, you have a 1,200 kilogram car.
Yeah.
That is 2.30 plus. What else do you got here? You got.
What about the 2.5 meters from the front of the car and the
Yeah, we're
3.45?
gonna get that. We're gonna get that number here.
Is it 2.5 and plus 3.45, or do those multiply out together?
We've got two people sit in the front of seat 2.8 meters in front of the car, and three people sit in the back seat 3.67.
Mm-hmm.
Okay, so we're using the front of the car. Okay, so then you got this. You got each person has a mass of 80 kilograms. So you got 2 times 80 times 2.5 plus 3 people times 80 times 3.45. So it's like we're just doing it from the front of the car here. There's the front, and there's the first group of people, there's the second group of people, and then there's the actual mass of the car at a certain position, all over 1,200 plus 2 times 80 plus 3 times 80 to get your center mass.
Oh, okay. I see what you did there.
So I get 2.49.
2.49. Okay. What should the units be?
Units will be in meters.
And meters. Okay. Correct. All right. Number 6. All right. Before we go further, what about in what direction will the boat move? Is the heavier person going to make it move, or what's going to happen?
I couldn't tell you. I got to look at the problem. I have no idea. These are really weird. That you, if you saw it, you would know, but I don't know. So, how far will the boat move? Boat initially at rest. The two people have been sitting at opposite ends of the boat. Now exchange seats. Okay. So there's only two people. This is this problem. Okay. So they usually draw it like this. There's a boat.
Yeah.
You have a person here, another person here. And they tell you how far apart they are, which in this case is 3.2. And you choose like this to be 0. Okay, so you got, this is the 80 guy, and this is the 56 guy. So this is, we'll try solving this here. So we've got 80 times however far it moves equals 56 times the length of the boat, 3.2 minus x. And we need to solve that for x. Then we got to find the new positions once they swap. So we got to find the original mass, and then we got to find the original center mass, then we find the new center mass, and we compare the two. So we can solve this for x. Let me pull up a calculator for this. So x is 1.32.
Will it be in meters or will it be in centimeters?
Yeah, meters, but that's not the answer. That's just the first part of it.
Oh, okay.
So then the next thing we do here is they say let y be the center of gravity. Why did they choose that number? It doesn't make any sense. Yeah. I gotta look at this another reference here. Let me try this another. So the original center of mass is you have 80 times 0 plus the mass of the boat, 63 times its position, which is 1.7. Sorry, 1.6 because it's right in the center, plus the 63, the 56 kilogram guy times 3.2, all over 80 plus 63 plus 56. Let me calculate that number, and then we'll see if we can get this to line up. So that's 63 times 1.6 plus 56 times 3.2 all over 80 plus 63 plus 56. Okay, so that's 1.41. Okay, so now they switch positions, and it changes the
Direction of the boat?
well, the boat moves. Okay.
Yeah.
So it says after it moves, this person, or the person of other mass, they're moving some distance L. So 56 moves some distance L, and then why does it do in terms of G? 8. Oh, it's a 9. Is that a 9? Yeah. So then the person, the 80 kilogram person, he moves. So it says 2 point. So he moves 3.2 plus L plus the mass of the boat now, which is 63. And they go, it's 1/2 of 3.2, which is 1.6 plus L, all over 56 plus 80 plus 63. So I'll solve this. I'm just plugging this into Wolfram. It'll do the solving of this. And I usually use X instead of trying to get it to use another variable.
Probably simpler.
Yeah. So plus 63 times 1.6 plus x all over 56 plus 80 plus 63. Okay, so it says negative 1.3, negative 1.38, and that just means it moved left.
And what units will it be in? Centimeters or meters?
Meters, because that's what it originally gave us.
Okay. Says incorrect.
Okay. Well, I don't know. I could have made it. There's so many places I could have made a mistake here. So check. Oh, I have the wrong number. I supposed to use 1.41. That will change the answer significantly. Okay, try minus 0.38. Or I guess it's just the distance it moves is just 0.38. It's just positive.
That works.
And it moved in the direction of the I had the 80 guy on the left, so I'm assuming that's there. So it moved in the direction of the 80-pound person.
Yeah.
Okay.
Do you want to do the center mass one just for 7.5?
Which one?
The should be the 9th one.
7.50.
Mm-hmm.
I cut out some of the numbers, but I probably.
It has 0.5 on the bottom and 0.25 between the 1.5 and 1.1.
Okay, let me see if I can. So you got M here.
Mm-hmm.
And you got 1.5. Those are how far apart?
Those are 0.5 meters apart.
And then the 1.1 is 0.25 apart?
Yes, correct.
Okay.
All right.
So what are we doing here?
Find the center mass of the three mass system shown in the figure.
Relative to the 1.05 to the one on the left here?
Yes, correct.
Okay, well, you choose that to be 0. This is the most straightforward question. The center of mass is 1.05 times its position 0 plus 1.5, the new mass, times 0.5 plus 1.1 times 0.5 plus 0.25 all over the addition of the masses together.
Awesome.
So we get these 1.5 times 0.5 plus 1.1 times 0.75. 0.75 divided by 1.05 plus 1.5 plus 1.1. Okay, 0.43.
0.43 kilograms.
Meters. Center of mass is always a position.
All right. Correct.
Okay, that will be a great place for us to stop. Thanks so much for scheduling, and I'll see you next time.
Have a nice night, Matthew. Thank you.
Bye now.